So how do machines learn? How do machines learn? Ryan's law.
Good evening, everyone. Tonight I am going to talk about how machines learn. My goal is to introduce one method that machines use to learn in the modern day, as well as go into depth about it and also difficulties that would come up when you use this approach. The method that I'm going to talk about today is called linear regression. So the most helpful resource for learning about linear regression would be the handout that you have in front of you. So if we all take a look at the handout, we will see a graph of housing prices with price and house size, and then a line, a best fit line that is attempted to be drawn right through all of the points. The way a best fit line is calculated is it has the goal of reducing these. If you see there's one point that has a marker that goes up to the line, that's how far away the point is from the line. And our goal is to minimize the differences between this line and all of the points. Coincidentally, that means that the line could potentially not pass through any of the points. And if there wasn't a relation between the points and the data, then the line wouldn't be representative at all. So the goal is to find the best line that represents our data. So then from there, the machine could say, what is the price for a 40 square meter house? And it would go along the line, find the location of how much the price would be, and then find that on the y-axis. So that is how a machine could predict a housing price. If I fed a machine lots of housing data that has the size of the house and how much it costs, they could draw a line through all of that and then predict the housing price by going along their line. Now, the first to mention about this graph is that a 40 square meter house would only be 400 feet. So these are not actual housing values. This was just an example. Looking at some of the smaller houses, I think that they would have been around 100 or 200 square feet, which is probably what a lot of millennials are living in now, with at least 5 people. So that explains how a machine would find it for one variable. But machines could take this much further than we can. They could take 15 variables and mathematically create a line that would best relate all of these data points to our goal of predicting housing price. So that's one helpful thing that computers can do that we wouldn't have been able to do otherwise. So that's why this method, which has been around for a while, becomes possible for machine learning models. So now I'm going to talk a bit about the difficulties that we would experience with machine learning. I have my excellent set of housing data. I compiled 300 different houses in the Waco, Texas area, and I figured out that my house is 300 square feet and that it costs, let's say, $50,000, or not 300 square feet, let's use 3,000 square feet, $50,000. So I have this excellent set of housing data and this excellent predictor that predicted a very accurate value. So now I want to use this house predictor in the Bay Area. So I take my model and I bring it over to the Bay Area and someone says, how much is a 3,000 square foot house going to cost? I say to them, well, that'll be about $50,000. And they check Zillow and they laugh a little bit and then cry a little bit more. But you can see that that was a simple example where the data wouldn't properly represent the actual task at hand. For housing prices, the location varies a lot, but there could also be more subtle things. For example, one thing that I'm really interested in is BART. I think transportation analytics are very, very interesting, very complex. So we wonder why I'm taking my 4:30 train out from the city. The city has less traffic at 4 than at 5, but at 5 they're running a train every 5 minutes, whereas at 4 they're running a train every 10 minutes. Yet the trains at 4 seem to be more packed than the trains at 5. So I wonder, why would that be? Because there's going to be less people. But I don't know if you've heard of this or not, but there's a concept where if you're getting on at the beginning stops of the San Francisco stations where you wouldn't get a seat, where you might not even get on the train, you could actually go back a few stops. I believe BART only tracks you when you scan your Clipper card. When you go back a few stops, they're not adjusting any part of their model. So they aren't actually tracking that at 4, they might have many passengers who would have been closer to the 3 o'clock slot taking up 4 o'clock trains. So that's an example of how the models for the transportation, the number of people moving, wouldn't be accurate because they didn't have the data that the people that went at 3 just took longer and then still went back on the 4 o'clock trains. So I will now talk about a few of the biggest examples that have happened recently with this. There was in China, for a lot of big cities now, their goal is to use artificial intelligence in order to identify jaywalkers and post their images on the internet, quickly find them, and then punish them. So there was a Chinese billionaire who his image appeared on this, and he said, "That's not me." So they looked at the camera that identified him, and his face was on a passing bus. Here is this guy, here is his bus ad, and here is his jaywalking picture. So with that, I will conclude. I hope that it made sense how machines could use linear regression to accurately predict the prices for houses as well as other things. And I hope that you found the examples of AI failure amusing. Thank you.